All right, go ahead and hand in your warm-up, please.
I was like,
Yeah, go over all three.
so those are your gems? Yeah. I forgot it was pajama day, otherwise I would have worn a t-shirt and sweatpants.
All right. So this thing, you might look at this and say, "Oh, initially awful," but once you start reasoning it through and you think, "Oh, right, derivatives are slope. I can do this." What's the slope way out here on the left? A little bit positive, so you're going to be a little bit above the x-axis. And then you continue to be vary a little bit positive until you get closer and closer to this vertical asymptote. And then what happens with the slope as you get closer? It gets steeper and steeper and steeper, so the slope gets higher and higher and higher in the derivative graph until you get to the vertical asymptote, and then effectively this is basically vertical, and so the slope is basically going off to infinity. So as you get closer to the vertical asymptote at 2, the curve does that. So what you see here is almost identical to what you draw over here. What's tricky is then when you come out of the vertical asymptote, now in what direction is your curve headed? Down, so the slope is negative. And initially, how negative is it? A lot negative. So you start off down here, and then as you proceed to the right, what happens with the slope? It's less negative. Now, it's still always negative, so you're always going to be below the x-axis, but you're getting less negative, so the curve is getting higher below the x-axis. So that's one of these things. And then right at x equals 2, this curve is not differentiable because it's not continuous, and so you have a discontinuity. Whenever you have a vertical asymptote on f, you will also have a vertical asymptote on f prime, and so on. Any questions with that? Number block 2. So the first half of the numerator is trying to tell you what your function is. And people. So what's the function that we're differentiating here? So 2, and then this whole thing is just a stand-in for x squared. And then plus 4. So that's our function. And then this is the derivative not at any old x, but at a particular value we'll call c. What's that c value? 3. So c is 3. And if you have no confidence in yourself, then you can double check and make sure you're correct. If you take this number and plug it into the function, you should get 22. So double check, 3 squared is 9, times 2 is 18, plus 4 is 22. Hey, that's what we're subtracting. Great. Yes, sir.
So, part B, that's called alternate form?
Yeah, so this is the alternate form of the derivative. So both of these are a form of derivative limit. This is what we know and love, that we spend a lot of time on. And this is an alternate version that we haven't spent as much time on and is a lot easier to use. It's called the alternate form of the derivative. The derivative. So this is the limit definition of the derivative, and this is the alternate form of the derivative. Because if you think about the generic formula is 2 times, is f of c plus h minus f of c all over h. And so 3 is in the c slot. So that's why. Yeah.
No, I'm fine.
Number B. What's our function? Yeah. So in the alternate form of the derivative, the first half of the numerator is the function. So that's just root x plus 7. Root x plus 7. Done. What's c? 2. See that thing? See that thing? They're both screaming at you with c's. But if you still don't have confidence in yourself, You can check by plugging C in for x, see what you get. It should be this number that you're subtracting. So 2 for x, 2 plus 7 is 9, 20 minus 3. Hey, we're subtracting 3. So that's all that is. So on your quiz this week, you'll have a couple questions like this where we give you a limit. You say, hey, what's the function being differentiated and where? Also on the quiz this week, you'll have to work through one of those limits just once. I'll just give you a function and say, hey, find the derivative of this function using the limit definition. Work through the limit process. But otherwise, if I want a derivative, we'll use the power rule. Ryan? Nope. So this is just f of x minus f of c. Anything else? All right, questions from the homework that we want to look at? And I think this was 2.2c. The wrong set of notes. And that was what, 39 to 54?
Yeah.
All right, Laura? 45. So 45 was one of these where you have to divide it out before you can differentiate. So what was it? X squared, x cubed minus 3x squared over plus 4. All over x to the second. All right, what else? Anything else? Is that one? Okay. So, step one, what do we got to do? Divide or cancel out, or I heard one person say bring the x squared up. All of those are good. Let's do the dividing method. If you divide, then what's x to the third divided by x squared? And what's 3x squared divided by x squared? And what's 4 divided by x squared? 4 over x squared. And then we could rewrite this last term as 4 times x to the negative second. What's this thing's label? Still f of x. And now you can differentiate using power rule. So what's the derivative of x? What's the derivative of 3? And what's the derivative of 4x to the negative 2? All right, and then we can throw x to the third down the stairs of that particular term. What's this guy's label? F prime of x. So that's dividing it out. To help see with that initial step, maybe it's helpful if you rewrite this as 3 separate fractions. X to the third over x squared minus 3x squared over x squared plus 4 over x squared. Because this is basically distribution of division. If you wanted to do it a different way, some people may have rewritten it like this. 3x x cubed minus 3x squared plus 4 times x to the negative 2. Just if you're going to do that, make sure you turn division into multiplication, not into adding. So sometimes I see people do this. They want to bring the x squared up, and they do that. And that's not the same. You can turn division into multiplication because they're inverse operations. You can't turn division into adding because they have nothing to do with each other. So not that, this. And then you would distribute, and you end up in the same place, right? So here you would be subtracting the exponent 3 and negative 2, and you get to this step. Anything else? Yes. 54. All right. So 54, we have two over cube root of x plus 3 cosine x. And don't forget, label it or whatever it is. It's f. All right. Step 1, can we differentiate right away? No. What do I need to do with this first term? Rewrite it so that x is out of the denominator and also not a radical. So what will this look like? Yeah. So 2 times instead of 2 divide, and then x to the negative 1/3. Do you have to do anything with 3 cosine x right now? No, just let it be. And this label is still f of x. Now you can differentiate, so now I'm going to bring out the f prime. What happens with this term? Yep, so negative 1/3 times 2 is negative 2/3. Get good at subtracting 1. Negative 1/3 minus 1 is negative 4/3. And then what's the derivative of 3 cosine x? Minus 3 sine x. Because the derivative of cosine is negative sine times 3 is negative 3 sine. Then, we don't like negative exponents, so where can you rewrite this x? In the denominator. Now, some people want to do this. And that's not wrong, but it's super awkward. And there's no need for that, because you could also say this is the same as negative 2 over 3x to the 4/3. And that's a lot less awkward to write. So please do it like this. Don't have the numerator be the fraction over the x. Just go right to here. Just throw x into the denominator with the 3. What?
You're writing so diagonal.
And
Laura said, can we take the slope of that?
Whoops. All right. Anything else? Satisfy your question? All right. Dice. 4, 5, and 6. All right. Rows 4 and 5, and Prince is home, so we don't have to have a row 6 anymore. What? Do I have? Yeah, he's home. See?
all the time.
As in, this is home. As in, Upper Darby is home.
You have scissors.
No. Oh wait, yes I do. I forget. There's like drawers. Oh, Zelda, homework?
Oh, yeah.
Yeah, thanks. I guess I'll find out when you hand it in or not.
Oh wait, I turned it in digitally.
What?
I sent it to email already.
2.2c?
Yeah.
When?
Saturday.
False. I did not get that email. I got 2 other emails. I did not get 2.2. I got 2.1c. I think I got 2.2a.
Wait, oh, you see that?
But I didn't get 2.2c. No, I got 2.1c. Why are you cutting it out?
There are preparations in your book.
No. Yeah,
I don't have scotch tape. I've got masking tape.
Oh, then you got stapler. It's fine.
I have a stapler. Why did you cut it in half? Did you not want to hand in?
No, I thought I only wrote on the bottom half of the page. I forgot I went on to 2 pages.
All right, ignore that stuff for chapter 8.7. That's for my AP class. This thing, I think we did an example like this at the end of class on Friday. We'll pretend we did. Try another example like it. So here's a function. Find the points on that graph where the tangent line is horizontal. So think about what does it mean if the tangent line is horizontal? What does that tell us? And then what can you do from there? So yes. Nope. I forgot. Worked out well for me. It didn't have less to be great then. I should do that more often. What? Nah. I mean, yeah, you'll get that. We're doing this. We'll get here. We're doing this. You're going to get some ugly numbers for your x. Don't worry about getting your y's exact right now. Here.
I don't even know this one right. I literally looked at one example yesterday. Like, writing. Yeah. And then you set it equals 0, then you find the x, and then you put it, you try to find the y.
Well, that's like,
Okay, yeah.
Oh.
So what do we want to find? What do we want to find? Points. Where do we find now x? The point consists of x and y. Plug that. All right. So just going over this. Tangent line is horizontal. Tells us what? Slope is 0. So we see tangent line is horizontal. Horizontal line means slope m is 0. That's kind of key. And then, if we know that the slope is 0, what do we do now with the function? Differentiate it. Do you have to use your limit process to get the derivative? No. Only do that if I tell you to. The rest of the time, please just use your shortcuts. So the derivative, f prime of x, is what? 3x squared minus 4. And what do we now do with that? Set it equal to 0, because derivatives are slopes. So you have your derivative, and then you set it equal to the slope. You know the slope, it's 0, because we're talking about a horizontal line. So we set the derivative, 3x squared minus 4 equal to 0, and then you solve for x, bless you. When you solve for x, what do we get? 2 over root 3. What are we missing? Plus or minus. So it turns out there are multiple points, because remember, you're going to get a plus minus as the result of taking the square root on both sides of an equation. And now that you have a solution for x, we must be done, because you got an x equals something, so that's always the end of the line. No. All right, what do we still need to do? Yeah. The goal was to find points. Points are constituted by an x and a y coordinate. So you have your x, great. Now you got to take that and plug it back where to get your y? F of x. So once you have that, you remember, oh yeah, y is f of x. So you're going to do y equals f of positive 2 over root 3. And you'll do y equals f of negative 2 over root 3. And because our x's are ugly, and you're plugging them in, you're going to get something fairly obnoxious. So we're going to say our points of tangency are plus or minus, and let's just say 2 over root 3, comma, f of 2 over root 3. How does that sound? All right, so we'll just do that. And negative 2 over root 3, comma, f of negative 2 over root 3. Unless anybody really wants to find out what that value is. Anybody really want to do that? It sounds like a hassle, so I'd rather be not. All right, this is good. Now let's go back, redo the problem, just adjust it minorly. So go ahead, do this again with x cubed plus 4x. Does anybody need this stuff up here still? Yes? All right. Normally, I would want you to find out what the y value is. It's just that in this particular scenario, we'll say we can't be bothered. All right, so George, is it cool if I erase this up here now? All right. So same idea now, but slightly different function. See what happens for us this time. All right, so probably about a third of you at least heard that conversation. So let's just talk about it. So our derivative, same thing, but now plus 4. When we go to set this equal to the slope, we have 3x squared plus 4 equals 0. Maybe subtract 4, divide 3, and then when you go to take the square root of both sides, please notice you're square rooting a negative. And so what does it tell us about our x solution? It's imaginary. So it'll still be 2 over root 3, but now it's an imaginary 2 over root 3. So it could look like that, I2 over root 3, or 2i over root 3. Do we bother worrying about this then? No, because we want points on a graph. Can your points involve imaginary numbers on a graph of f of x? No. So this would mean no points on f of x have a horizontal tangent line. Because the only solutions for x where you have a horizontal tangent line are imaginary. And that's just nonsensical. You can't have imaginary points on a graph of a function. So you just stop there and say there are no horizontal tangent lines to f of x for that reason. So that can happen to you. Any questions to follow up on this idea of horizontal tangent line? So there is no tangent line that's horizontal because the only way for us to get a horizontal tangent line and make the slope 0 is by having an imaginary x value. Can't really plot that on a graph, so no tangent lines are horizontal. There are lots of tangent lines to this curve, but none of them are horizontal. Any other questions with that? All right. The rest of class, probably we're going to look at some applications. So basically take what we're doing and shoehorn it into physics now. Lucas, could you kill the back light switch, please? And you don't need to write the stuff in italics up at the top. Just read that. And then the notes that you are going to probably want to write, maybe start here and follow. And we're going to have a few examples that are also just going to be up there on the overhead, because the word problems, I don't feel like writing them up on the whiteboard. So, we have a lot of ways of expressing ourselves with regards to slope. We can use the word slope. We can use the term rate of change. We can use the word derivative now. And they all mean more or less the same thing. There's a difference between average rate of change and instantaneous rate of change. Average rate of change is what you're used to doing. So like your average velocity, your average speed over a period of time, that's an average rate of change. So you see how fast did Usain Bolt run in the 100-meter dash when he set the world record. You would take 100 meters, you would divide it by the time it took him, and there's his average speed. But that's not the actual speed he ran at every second of the race. He starts from a speed of 0 right out of the blocks, and then he probably reaches his maximum speeds around meter 70 or 80 or so. And then because he's Usain Bolt and he has such an enormous lead, he slows down into the finish line because he can do that. And he still sets the world record because he's amazing. So his instantaneous rate of change, his instantaneous velocity at any given point is not going to necessarily equal his average speed. So you have this difference between the average speed versus the speed at a particular moment in time. That's what instantaneous rate of change or instantaneous velocity is. That's the derivative. Average is just kind of a slope over some period of time. So when you're asked to find an average rate of change, and you'll still be asked to do that sometime, an average rate of change is a slope over some period of time. And you just do your slope formula over that time period. An instantaneous whatever is a derivative. Now, it's not always like position and velocity. Sometimes it's population growth rates, which you'll do for, like, if you're a biologist, you're doing that for like fruit flies and bunnies and fun things like that. If you're a demographer, you're doing that for humans, and you're looking at birth rates and death rates and immigration rates and like how is the population growing over time for a country or a state or a city. Production rates is going to be something like producing things on the factory floor, like making cars or making shoes at a sweatshop or something. And how many? They don't have to be cheerful examples. Like how many sneakers do you make per hour, right? That's a production rate. Or water flow rates, you turn on the faucet, water comes out. And you turn on the faucet some more and water comes out faster. So that's a water flow rate. They use that sort of math also in civic engineering for dealing with the roads. And they use water as like an analogy for cars on the highway. And it works out pretty well, actually. And then there's velocity and acceleration, which is what gets used for most notably physics. So we're going to start off in velocity and acceleration land. But all those other things will show up once in a while over the course of like the next 18 months of calculus. What? Huh? If you move on to Calc AP or PC next year, you'll be at one point or other talking about the rate of water flowing into or out of a cup, or a tub would make more sense, or population growth rates of like a city. So in acceleration and velocity land, that's going to be what we do down here. We're going to focus in on velocity first of all. We'll save acceleration for a later day when we start talking about second derivatives. We're going to use S to represent position because that makes sense. And we have a position function S of t, where t is just time since you started, S is position, and then the rate of change of the object over some time would be the average velocity. And that's what we have down here. And then we have like the specific equation for an object in free fall, which if you've done physics, you know your Bokerstov equations. This is where those come from. So down here, I'll scroll a little bit, and we'll have our equation for object in free fall, what are the components of it, and then we'll look at some examples, see how do we use it. So get down to here, and then pause, and I'll scroll when people are ready for me to scroll. Can I scroll yet? No. Well, I'll at least scroll past this stuff on the top. And then that's the end of the notes, and then we get a new example there at the bottom. And should have included this in here, but I forgot to. If you want to get the major takeaways from general example, average rate of change is just going to mean your slope formula over some time interval. And instantaneous rate of change will be the derivative at some point. And derivatives are slopes, so these are effectively the same thing. The difference is, are we looking at some interval of time or at a particular moment in time? And if you're in physics or taken physics, you guys have seen this equation here? Yes? Something like that? Okay. So this is an object in free fall, and S, again, is the height. So this is a function. This isn't S times t. This is a function S of t. So this is your height at time t after we've dropped or thrown or launched some object into the air. So like we go up to the roof, we shove a freshman off the roof, and there's his height. This first term out front is making sure things go down. So that's why it's negative. That's gravity. V0 is pronounced V naught, and that's your initial velocity. That multiplies time. And then this plus S0 at the end, that's pronounced S naught, and that's your initial height. If you drop an object, what's the initial velocity? 0, because you just dropped it. You didn't give it any initial impulse. You just let it go, and gravity does its thing. So if you drop an object, your initial velocity will always be 0. If you jump or throw or launch an object, you have to read carefully, and you might have some sort of upwards velocity. This is all moving in an up, down, y direction. So this isn't involving any side-to-side movement. This is only involving straight up and down movement. So if you like jump off a diving board, there is some horizontal movement so that you don't like crash back down in the board and injure yourself. We don't care about that horizontal movement. We only care about the vertical up-down movement with this equation. So in physics, they'll work on the y direction and the x direction movement. In here, we're just talking about straight up and down stuff. Time t is just the time since we launched you or threw you or dropped you or whatever. And then s is this s, and that's your final height at whatever time we're talking about. If you want to work in terms of meters, it's the same equation, except instead of -16, we deal with -4.9. So this is dealing with feet and seconds, and this down here is dealing with meters and seconds for your position and time. Any questions with anything before we get into specific examples? Friends?
What is
So the really generic form, because this is specific to Earth, if we wanted to go to like Jupiter or Pluto or something, we could do a little bit different. So it's -1/2 times g, where g is the acceleration due to gravity, plus t squared plus v naught t plus s naught. So on Earth, the acceleration due to gravity is 32 meters per second squared. Half of that is 16. Or in meters, it's 9.8 meters per second squared. Half of that is 4.9. And it's negative because gravity pulls you down. And down is negative direction and up is positive. So the 16 is just coming from gravity on the moon or some other planetary body with a different mass and therefore a different gravity. You're going to have a different number out front of the square term. Now we need this still. We're good. What's the ratio of 1 meter to number of feet? This is a meter, and it is 39 inches and maybe another ½ inch or so. No, not even 39 and a half. It's like 39 inches and a tiny bit. So 3 1/4 feet roughly to a meter. Are you trying to double check and make sure it's legit? No, that's a meter stick. It's a yard plus a few inches. Yeah, because a yard is 3 feet exactly. That's 39 inches to change this. 36 inches to be a yard. Check. I guess you could double check this. Like take 16 divided by like 3 1/4. It should be about 4.9. Now I'm curious. All right, 16 divided by 3 1/4. Yeah, it's 4.923. Like the 16 and the 4.9 are both rounded off. These are not exact answers. This is good enough for physics and engineers. If you want to be really, really precise, then you take it out to like more decimal places. But for most purposes, that's fine. In the conceptual physics class, I think they just make this 5 to make the math a little bit easier. All right. Example. You drop a ball from a height of 100 feet. And let's do that. And then do that. All right, cool. So in part A, we're finding the average velocity over some time interval from 1 to 2. So this is the interval times, this is beginning time and ending time. And we want to find the average velocity. And remember, average velocity is just the average rate of change of your position. So average velocity, average rate of change of position, same thing. So what we're doing to find the average velocity is we're finding the slope of our position over the interval from 1 to 2. So maybe write down for the first time you do this, average velocity equals slope of position over given interval. Because velocity is just the change in the position, either at some particular time or over a period of time. When we're talking about average velocity, it's over a period of time. So we got to know our slope formula still. And what's our slope formula? Yeah, y2 minus y1 over x2 minus x1. Now, in this particular example, instead of y, what letter are we using? S of t. So y2, what's our, well, let's talk about the bottom first of all. Instead of x, what letter are we using? Time. And what's time 2 for number A? What's our interval? 1 to 2, so what's our time 2? And what's our time 1? 1. In part B, what's our time 2? In time C, what's our time 2? Okay, so this gives you your times. That's time 1 equals 1, and time 2 equals 2. And we're using time instead of x in the particular example that we're doing right now. So up top, y2 is going to be s of 2, and y1 is going to be s of 1, your position or height at time 2 minus your position or height at time 1. So then you just go into the function for position and do it. So what's s of 2? Go. Arnor, what is it? You got 48? That's your final result. Maybe. What's just the height at time 2? Yeah, plug into, what do you get? 36, all right. And Prince, what's our time at time 1? Okay, well, you can do this in your head. What's our time? What's our height at time 1? 84, yeah. So s of 2, you plug in 2, you see what you get back for your y, there's your position. S of 1, you plug in 1 for time, you see what you get back out for your height. For s, there's your position. So s of 2 minus f of 1 on the denominator, 2 minus 1. I think we can all do that. And then, what's 36 minus 48? What did I say this? 36 minus 48, that's an 84. What's 36 minus 84? Negative 48, right? So there's a velocity. There's our average velocity over this interval of time. So from time equals 1 to time equals 2, our ball is falling at an average speed of 48. What are the units for the speed? Feet per second. So feet per second. If you're like unsure, the numerator is measured in feet because that's position, and the denominator is measured in seconds. So feet over seconds is feet per second. So that's our average velocity on this time interval. Why is it negative? Because it's falling. It's going down. That's a negative direction. So if you're like interpreting positive or negative, if you have a negative velocity, you're moving in a negative direction. That means you're, in this case, going down. If you're in a horizontal world, negative would be to the left. Now, go ahead and do it again for yourselves. If you're male, do B, and if you're female, do C. So that we like split it up, and then we can have everybody share back what they got. So do it again for B and for C, and then we'll find the instantaneous velocity altogether right at the time equals 1. All right. Menfold. What's the S of 1.5 value? 64. So what's 64 minus 84? Divided by 0.5, and we get negative 40. So negative 40 feet per second. So we squeeze the time interval towards x equals 1, and our speed slows down a little bit. Our velocity increases, but our speed slows down. That's a little confusing, maybe. Women, what is our average velocity over the interval from 1 to 1.1? Negative 33.6. Anybody want to argue with that? Okay, cool. So if we're asked, hey, what's the average velocity of this whatever it is over this time period, you're just doing slope over that time period. Get your y's, subtract them, divide by the width of that interval. Now, if we want to find the instantaneous velocity right at time 1, you could continue this process and do the limit as time approaches 1. We've got time for that. So if we wanted to find the instantaneous velocity right at time 1, what would you do with your position function? Not set it equal to 0. Take the derivative. Yeah. Instantaneous velocity is derivative. So when we see instantaneous velocity, you say, I'm going to do a derivative, because that is velocity at any time. What's the derivative of this function? Negative 32t. And so we want the derivative, or the velocity, right at time equal 1. So we say s prime of 1 or v of 1. Same thing, because the derivative of position is velocity. Just plug in 1 for time, and we get negative 32 feet per second. Any questions with A through D of just dealing with velocity, average versus instantaneous? One is a slope, one is a derivative. Otherwise, it's the same idea.
So when you take the derivative of the velocity equation, and then you set that equal to 0, you solve it.
But if you're setting when the derivative equals 0, is that what you just said?
No,
Say it again. Say it again.
the way you take the derivative of the velocity equation,
Yeah.
and you set that equal to 0, what are you solving?
So the derivative of velocity is acceleration. We'll talk about that later this week, maybe. And so then, if you set that equal to 0, you're solving for when the acceleration is 0. Which, in this case, never happens until you hit the ground and are no longer moving at all. At which point, your position function is now a constant function. You're always at a height of 0. We're not done yet. Back to here. Find the time needed for the ball to hit the ground. Let's think this through. The time needed, what do we want to have happen? The ball to hit the ground. When the ball hits the ground, what is its height? 0. So height is represented with what letter? S. So that's S equals 0. So which function are we using? Original function or derivative? What equals 0? S. So which function are we using? S. We're using the height. If the ball is going to hit the ground, the height needs to be 0, not the velocity. So if the ball is going to hit the ground, and we want to know when does that happen, we want the height S to equal 0. So we would then say, all right, take the position function and set it equal to 0 and solve for time. And that'll be how long it takes for the ball to hit the ground. Basically, how long is it in the air? Now, once you know that time, if you want to know the velocity at impact, what do you do with that time? Now you use your derivative, because now we're talking about velocity again. So if we're talking about height, we're talking about S. We're talking about velocity, we're talking about S prime. So keeping those two things straight. It's like Y versus M. If you want to know when is the ball going to hit the ground, use your original function. If you want to know the velocity at that time, use your velocity, your S prime. So you have one of these sort of things on your homework. We'll do more of this sort of thing tomorrow. And I'll see you guys tomorrow. Have a good night. Your homework is due tomorrow. Make sure you do God's maps. Yes, sir.